In section 6C, we're going to look at some metric graphs and the standard deviation. In section 6B, we did introduce the idea of using a standard deviation to describe the spread of data in a graph that would be symmetric, but we didn't really get into the details on how you could apply it to really analyze that data. Most graphs that are symmetric are not going to be perfectly symmetric. Just as you collect raw data, the idea that it's perfectly balanced around a middle number is not going to be, so likely. But if it was, you'd get a graph that we refer to as a normal distribution. Okay, and that's what we're looking at here as a picture is a perfectly symmetric graph. Again, remember that in a symmetric graph, the middle number could either be a mean, a median, or a mode, but we tend to go with the mean for this. Okay, so normal distributions are going to be perfectly balanced around that mean. Just that's your high point, and then it slopes evenly around it. We sometimes refer to this as being a bell curve. All right, so what's neat about normal distributions and standard deviations? Okay, the standard deviation is a measurement that best approximates the distance that you are from that center value. Okay, and the little symbol that we're using down here is called sigma. It's a lowercase letter, Greek letter. You don't have to know that, just notice standard deviation. As I move forward in the notes, you're not really going to see that symbol anymore. All right, this, in our graph that we're looking at right here, this is the mean that's right in the middle, and then this dotted line here goes down to where it says plus sigma or plus standard deviation. But then over here you see plus 2 sigma or plus 2 standard deviation. So the calculation of the standard deviation, they're using it to measure out one length of a standard deviation or one distance of standard deviation out to here. But then they're measuring again out to there. Then they're using that to measure a third time out to this spot. And if you notice that in the graph as you move out, once you get to 3 standard deviations in both directions, you basically have the whole graph consumed here. Now I say basically because I know that there's this teeny bit of the graph that's just past that outside line. Okay, but here's the really neat numbers that we get out of this. If you were to measure 1 standard deviation to the right and 1 standard deviation to the left, you're going to get this space here, which comparable to the rest of it is a good amount of the space. Right? It's actually about 68%. Now it's not exactly, but it's about 68% of the data. So what that tells us is that 68% of the data collected in this symmetric distribution is going to be within 1 standard deviation of the center. All right, when you go out to 2 standard deviations, out to here, you're only missing this little bit of space on the edges there, and that all adds up to 95%. So now we've got almost the entire thing. All right, and if you go out 3 standard deviations, out to here, you've got 99.7%. You basically have everything. There's just this 0.3% that happen to lie outside of 3 standard deviations. All right, so for problem number 1, the intention was that you were going to look at the graph and you were going to observe as many things as you could from it and then answer the questions. But basically, in my discussion of it, I pretty much covered all of it. But I'll go over the answers anyway, just make sure that you do have them. Question A, the distribution is symmetric about the mean. That's something that we're going to see in a normal distribution, and that'll also be consistent throughout the entire activity that you see here. About 68% of the data will be within 1 standard deviation of the mean. About 95% is going to be within 2 standard deviations, and about 99.7% is going to be within 3 standard deviations of the mean. Okay, and if those things don't make a lot of sense yet, don't get worried about it. This is pretty much what the whole activity is, and we're going to go through example after example until we kind of beat it to death, and I think you have a pretty good idea of what it is. Oh, and by the way, this activity happens to be one of my favorite activities that we do. I think there's a lot of value in understanding that the information that we get at the end, which is called percentiles. All right, so problem number 2. All of the questions that you're going to be answering here are going to be based off of this graph. And I do want to point out from the very beginning that this is not a symmetric graph. This is actually more or less like skewed to the left. The main reason that it is, though, is because you've got this one high point that's there. If this were to drop down to about here, you would get a fairly symmetric graph. So I don't know if this is a great example to use, but we can still get through the problems. And then after that, you're going to see this consistency in things that would be more of a normal distribution. All right, in the picture, I'm going to go ahead and talk about the stuff that I do have marked off because it goes along with all the answers that you're going to see here anyway. The mean calculates to be right here, and that's what I did as the blue line, and then all of the pink lines are going to be standard deviation measurements. So this might be hard to tell what I was writing, but that is 1 SD. So I just called, instead of calling it sigma, I called it SD for, standard deviation. All right, so that'd be a measurement of a standard deviation to the right and one to the left. You're going to notice that the distance in either direction is the same thing, or they should be. I mean, you're drawing this by hand, but they should be the same. And then that same width is what you would be using measuring out to the next standard deviation. All right, so let's see how I got these numbers here. Up at the top, it tells you that the mean is 162.74, so that's how I got that blue line that I drew there. Question A wants you to figure out one standard deviation below and above the mean. So all you do is you take your mean number, which is the 162.74, and then you're going to add or subtract the standard deviation to it. The standard deviation in this case was 9.3. Now, you might recall in 6B that we didn't talk about how you calculate standard deviation, so go ahead and expect that. These are two things that will be provided for you. You're going to get the mean, and you're also going to get a standard deviation, so don't worry about doing any of those calculations. Maybe we'll have you do the mean a couple of times, but a lot of it we'll just go ahead and hand you that stuff. All right, so if you add it on, you're going to get 153. Why did I write 153? That's not going to be correct. I think I just wrote them backwards here, because I know my picture's good. All right, so if we subtract, we're going to get that, and then if we add, we're going to get that one. Well, at least it's authentic as you're seeing the notes here. All right, so B, draw a vertical line in the histogram that estimate like where these standard deviations are. So I drew them there. And then it asked this question that I really wasn't too sure how to answer. It says, estimate the percent of these women who had the heights within one standard deviation. So I know that that's coming back to like getting at this picture, like how much is within one standard deviation. Okay, so I know that they want us to start thinking, oh, it's about 68%, but the picture's not a normal distribution, right? So it already doesn't quite fit on it. So I wrote this, said, well, because it's not symmetric, I'm gonna say it's less than 68%. So I'm basing the answer on what I know from the normal distribution, but because I've got this high point that's sitting on the outside, I was like, look, it's probably gonna be a little bit less than 68%. So I wasn't too sure on that one. Don't know if you can hear, but there's a lot of thunder in the background as I'm recording this. All right, C, we're gonna go ahead and calculate the actual percentage. So then they tell us that, look, within that standard deviation, 119 data points or values were there, and we had a total of 180 data points in the whole distribution. So if you take the 119 and you put it over 180, you're going to get your fractional amount, which of course is your percentage, and it turns out to be 66.1%. So it is close to the 68, but again, because you have that high point on the outside of it, some of that percentage is going to move to the outside versus being within that one standard deviation. All right, so D is going to have us do the same thing with two standard deviations, everything that we just did. So 162, you're going to add on to 9.3. So you can just add it twice if you want. You can take your last answer and you can add 9.3 on it, however you want to do that. But it does get you up to this number. You're also going to subtract two standard deviations, which takes you down to 144. They tell us that 175 or with 175 of the 180 are within the two standard deviations, which turns out to be 97.2%. 2%. All right, let me take a look at the graph here. These are the 2 standard deviation measurements, and you're going to see that we pretty much have taken all of the data that's within this. That's that 97.2%, and of course the numbers are measuring for pretty far out for those. All right, E, based on normal criteria in the box in the previous page, we ask whether the data is approximately normal, and I'm just, I've already answered that question here, that the numbers seem to look pretty close to what we need. Like 2 standard deviations would have been 95%, right? But because we had that one like high interval, I think it just throws things off a little bit, and definitely visually, it makes it not look like it's a normal distribution. So the bottom of page 2 mentions the 68, 95, 99.7 rule. That rule refers back to the normal distribution that we saw at the very beginning here, and what it says is that 68% of your data is going to be within 1 standard deviation of the mean. 95% of the data is going to be within 2 standard deviations, and pretty much all of it, 99.7% is going to be within 3 standard deviations of the mean. And that would be true for all normal distributions that we have. Not quite sure why they put it at the bottom of page 2, because it seems a little inconvenient, because you'll be using it for, the next page and then everything that follows right after it. So unusual place to put it, but that's fine. All right, so example number 3, we get to look at a normal distribution and start applying that rule, which I said before. I kind of enjoy these problems. I think they're fun here. All right, suppose that the heights of men are normally distributed with a mean of 70 inches and a standard deviation of 4. All right, so again, you get both of those numbers, okay? We have the mean of 70 inches, we have the standard deviation of 4 inches. So in a normal distribution, a graph that looks like this, you can mark off, so if you don't have any of the lines on there, you usually get these little dashes, and you can see those on your copy first here. The mean is going to be the one right in the middle, so I'm going to mark that off at 70. All right, then at each of these other dashes, I go ahead and just draw vertical lines all the way through for these things to block off the areas. Each of these is going to be a measure of that standard deviation away from the mean. So when you go to that mark right there, you have to move 4, in this case it's inches here, you have to move 4 inches in the greater direction, so that'll get you to 74. To get to the next one, you would move another 4 inches and then another 4 inches. The opposite direction, you're just going to be subtracting 4 each time as you go that way. All right, so we get all of these heights, which are going to be the transitions at the standard deviations. Okay, so question B, what percent of men have heights between 66 and 74? All right, so 66 and 74 are the numbers that would be 1 standard deviation in either direction. So that space together in the middle, here it is all highlighted there, is going to be that 68%. Remember, we got the 68%, the 95%, and the 99.7%. All right, so that is within 1 standard deviation is the majority of the data, 68%. Question C, what percent of men have heights outside the height interval in B? So if this is 68%, then we're asking about the 2 pieces that are on the outside, and the difference from 100% is going to be 32%. Okay, and then as you're answering all these questions, it's kind of neat to think about, what are these things actually referring to? This is the height of men, right? So this is that middle group, what we generally expect the height of men to be. 68% of men have a height from 66 to 74. These values here represent the people that you don't expect to see too often, the people that are taller and the people that are shorter. Question D, what percent of men are shorter than 66 inches? Okay, so what we're doing here is just dropping off the tall end here and just looking at, all right, what percent of people are less than 1 standard deviation away from the mean, less than 66 inches tall? That's going to be 16%, because it's half of the 32. All right, E, What percent of men are taller than 78 inches? Okay, so at this point, we're now looking at the very, very tall ends of heights, right? So 78 inches, you go up to the top graph, there's 2 standard deviations away from the mean. So there's my mean, and I went 2 standard deviations, would have had that line there, and I'm only looking at that tiny, tiny group that's over there. So not very many are gonna be that tall. Let's see, what is that height anyway? If we take 78, divide that by 12 inches, we get 6.5, which is actually going to be 6'6". Okay, so we're looking at what percent of men are 6'6" or taller here. Well, just taller than, not that, and then, but don't worry too much about that. Okay, so within 2 standard deviations is going to be 95%. So let me go back to this picture here. So our boundary is right there. That's the one that we're talking about. So within 2 standard deviations, you're going to have 95%. Okay, so that means that these remaining 2 pieces are going to be a total of 5%. But we only want the very top part. We don't want that really low one there. So we'll take 100 minus the 95%, leaving it 5, but then splitting that in half, so that you get 2.5. This is only going to be 2.5% of the population. All right, F. F is a neat question because you're putting together the answers that you previously had, more than just splitting things in half. All right, what percent of men have heights between 66 and 78? So 66 was that bottom line that went with the 68%. And the 78 is the one that we were pretty much just looking at above. That was right here in that transition. All right, so the way that I did it, I took 95% because that would be within 2 standard deviations in either direction. So that's going to be all of this. Okay, so I knew it was going to be less than that, but I took the 95, sorry, took the 95, subtracted 68 from it. Okay, and so that's the 68. When I subtract that, what I end up figuring out is how much the wedge here and here would look like. Okay, so I take out the 68, which is all the way up to there, from the 95, and that leaves me 27. So this piece right here plus this piece right here are going to be 27% together. All right, now if I split 27 in half, I'm going to get 13.5. I didn't really show it here, but it would be this number, the 13.5. So now I took 68 and I added on half of the 27, or adding on 13.5, and I get 81.5. You could also, as I'm thinking of it right now, once you figure out that one of these pieces is 13.5, once you figure out that part, you could also just go to 95 and then subtract that piece. So there's a couple different ways to do it, but let me add it to this just to make sure you visually get to see it. 68%, if you split that in half, you're going to get 32. Each of those is worth, no, it's not 32, it's 34. If I'm going to do it, got to do it right. All right, you split those apart, they're each going to be 34. And what I figured out about these two is that if I take 95 and subtract 68, I get 27. All right, and then when I divide that by 2, I get 13.5. So each of these is 13.5. All right, and then you could do a similar thing for the outside part. You know that that's all worth 99.7. You could subtract the 95, split the difference, and then you got that one. So if it helps, you could actually figure out all the numbers of the individual pieces and just have that as information that you can use. All right, then the last question, I was a little underwhelmed about it. It just says, if you took a group of 1,000 men, how many would we expect to have heights between 66 and 78? Okay, so we did all the work up there to figure out that it's 81.5%. So if you multiply 81.5% times 1,000, that's just going to shift the decimal over 3 spots and you get 815. We probably could have done something a little bit more challenging with that, but maybe it does get the point across that these are percentages and then what that means to a population. All right, for the rest of the activity, what we're going to be focusing on is how we can find a percentage of a population or data that is not at an exact standard deviation. Like, the rules here are pretty nice, that one standard deviation is about 68% and two is 95. But what happens when a real data point is in between 1 and 0 standard deviations, or between 1 and 2 standard deviations? What percentage do we get from that? So we're going to talk about first what's called a z-score. Basically, a z-score is a standard deviation. What do we have? We're still going to talk about the heights. The mean was 70 with a standard deviation of 4. Okay, so a height of 66 inches has a z-score of -1. Okay, so where is that graph? All right, so the mean was at 70 and here's 66, right? It was 1 standard deviation below the mean. So it was 4 inches less, but it's also 1 standard deviation below. So the z-score is going to be -1. Okay, it's 1 standard deviation away, but it's also below the mean, so it gets a negative number. Okay, so that'll be one thing about the z-score that we might not talk too much about within the standard deviations, that above and below, you can either be positive or you can be negative. It was mentioned in 6b, but now we're really going to use that positive versus negative here. All right, so let's check out these. 78 inches is right here, which is 2 standard deviations above. So you said the z-score is 2. It's a positive 2, but you just write down 2. 58 inches is going to be over here, so that's 3 standard deviations below. So you're going to call it -3. All right, and then a little bit of a tricky one here, but 70 inches is the mean, right? So you're not anywhere away from the mean, so your standard deviation is going to be a 0. All right, question C, it says to label the distribution to the right with both the heights and the z-scores. Okay, so don't worry about any of the shading yet here. These are all the same values that we saw on the other graph, and we added on there, and then we knew that 78 was 2, we knew that 58 was -3, so we just go ahead and fill in all the rest of them. You've got 0, you've got 1 and -1, you've got 2 and -2, you've got 3 and -3, and so on. All right, D, suppose that we wish to know the percent of men that are shorter than 68 inches. All right, so when you look at the numbers here, 68 is not one of our numbers. It's not there. But we should still be able to ask the question, right? So here's 68. It's right between the 66 and the 70. So I drew a line there and I shaded the left direction because I wanted the heights that would be shorter than the 68. Okay, so that is shaded there. Then when they ask this question, why can't we use the 68, 95, 99.7 rule? Well, one, it's not on actual whole standard deviations, right? But it sounds convenient because 68 is right between these two. So I think what the question is getting at is, how come, why are we not allowed just to take this rule and manipulate it? And the main thing that you need to know is that the graph has this curved shape. It kind of bows out in this area, then it bows in that spot. So you don't really have what we call a linear change. It's not a straight line thing here. So you want to be really careful that you don't take this rule and start trying to split the difference proportionally in a way. Meaning that because 68 is halfway between these two, you can't, let me show this graph here. You can't look at the difference from 0% to 34% that direction and just split it down the middle and call it 17% and then start doing numbers on that. And that's due to the curvature of it. All right, but you can still talk about the z-score. The z-score is the measurement just horizontally across, right? So if you go half of a standard deviation away, so 2 inches is half of 4 inches, half of a standard deviation is still called a -0.5. So that holds true. It's the percentage part that you can't make any leaps into. For that, might be getting a little bit ahead of things here, you're going to have this table that was at the end of the activity that's going to relate all these z-scores that you can easily find to the percentiles or the percentages that are a little bit harder to do. Next part right here is going to talk about how you would get the z-score, the z-number, the standard deviation, whatever you want to call it, if it isn't something that is so obvious. Like the example that we just looked at with the 68 inches, it was obviously halfway from 70 to 66, so you could just call it 0.5. And if I didn't mention it was a negative, because it's going to the left direction, anything to the left would be negative. Okay, here is a way that you could calculate no matter what you get. So if you can't visualize it, if it's just kind of an oddball location of it, then just do this. You take the data value that you have and you subtract the mean. Okay, and you may remember that from doing one of the tables in 6B. We called it X bar. The mean was called X bar, so that might jog your memory. But you take the actual data value, you subtract the mean. So if you happen to be something that is to the left, and you subtract the mean, you're going to get a negative out of it. But if you take a value that's to the right and you subtract the mean, you're going to be getting a positive number. So that's the positive and negative working itself out. You subtract the actual data, or sorry, you take the data point, you subtract the mean from it, and then if you divide by the standard deviation, which is provided for you at the beginning, that gives you your z-score or your standard deviation for that. So 68, if you subtract 70 from 68, you're going to get -2. Then you divide it by your standard deviation, 4. That simplifies down to -0.5. So some of these are a little bit easy to figure out on your own by just looking at them and knowing the division of a standard, like the width of a standard deviation, if you could divide that up. But if you get some other things that are a little bit more unusual, and, then you could use this. All right, let's see, H. All right. Oh, I didn't realize we were going to do this quite yet. Okay, so then what H is going to do is now get us looking at the table, right? So we have an easy way to get a z-score, right? Just subtract and divide, and you get that number. Okay, but what would be the percentage that corresponds to that z-score? Okay, so now that we have a z-score of -0.5, what we can do is go to this table that's been provided for you, and like nobody ever does this calculation by hand. This is just something you go and reference that's already been figured out for us. And it's always consistent, so it never changes. What was it? -0.5. So right there, you have z-scores and you have percentiles. So you just got a bunch of columns here because we have a lot of numbers to look at. Right here is where you're exactly at the mean. If you have a z-score of 0, then 50% is above, 50% is below. These percentiles are always going to talk about what is to the left side, what is on the bottom side of things. So if you have really like larger negative z-scores, you're going to have very small percentiles. But if you have the higher positive ones, you're getting like a higher percentage that goes with it. So it increases, it basically measures what's below the line, whatever's to the left. Anyhow, getting back on track here, there is your 0.5, or -0.5. Okay, so you're going to get 30.85%. So a z-score of -0.5, -0.5 tells us that we have 30.85% that are below the 68 inches. All right, on the reverse end here, if we were to ask the question, what percentage of men are taller than 68, you would still have to do this thing here, right? You would still know that standard deviation, that z-score, and then you would go and find that number on the table. But because the table is always telling you what is on the left side or the bottom side of things, if you want the right side, you just need to subtract it from 100 and you'll get your number. All right, problem number 5 is going to have us look at some practice with z-scores and percentiles. For this example, we're going to talk about SAT scores, the math SAT scores in 2013. These were normally distributed around a mean of 514 points with a standard deviation of 118 points. Okay, now what you might not know is that SAT tests are actually designed so that they are normal distributions. At least that's like the goal that they have in mind. And what they really want is for the scores to have a mean of 500 points with a standard deviation of 100. Okay, and you'll see that they came pretty close here, that having the mean of 514 with the standard deviation. But that's how those tests are generally designed, and the way that most of us know them is just the higher the score, the better. But sometimes we don't really understand what the value is in a certain score and why colleges want a certain number for a score. But most colleges are going to want you to have at least a 500 in either part of the SAT, because if you're at the 500 mark, that would mean that you're in the top half of those people who took the test. In this case, it was actually 514, but data can be a little bit different because it's real. All right, so yes, getting back on track, but hopefully that was a little bit informative to you here. The mean is going to go in the middle. You're going to add and subtract the 118 from that number, just going out to the sides here. 868 is not a score that you're going to get on the SAT. I don't think that you can either get 160 either on there, but that's just what it looks like in the table here. All right, let's see what we got here. What is the percent of students that scored below a 650 on the SAT? All right, so let's get a ballpark idea of where that is. Based off of this picture, 650 is going to be somewhere in between these. It's actually going to be closer to this end here, so maybe I didn't quite draw the line right, but it is going to be sitting between 1 and 2 standard deviations. All right, so we begin by calculating a z-score, and to do that, you take your actual value, the 650, and you subtract your mean. So 650 minus the 514, and then you divide that. So I didn't do it individually, but then you divide it by the 118, which is your standard deviation, and that's your z-score, which turns out to be about 1.15. Let me type it in there because I want to see if I did any rounding with that. So 650 minus 514. Divide that by 118. All right, so I did a little bit of rounding down to the 1.5. Okay, so then you take that number, because that's a z-score. That doesn't really tell you a lot. And then this is where you get the real information from it. All right, you always want to verify that it's supposed to be a positive or negative. Because the 650 is over the 514, you are going to be on the positive side of things here. So I'm not looking at anything that's negative. All right, it looks like from the table that we have 1.1 and we also have 1.2. We're not going to get a 1.15. So when it comes down to these spots here, you sort of do what you want. If you think it's really close to the 1.2, you could just take that number. If you think it's very close to the 1.1, you can take that number. In our case, it seems to be right in the middle of these two here. So again, you want to be careful not to split the difference because the graph is curved. But for the sake of what we're doing, that would be fine. Just grab a number that's in between. So I went with 88 for that, okay? Which means that 88% of the students scored below that amount. And of course, like 12% would be above. Okay, so that number does have to be a little bit of the estimate. You're not supposed to just split the difference, like add them together and divide by 2 because it's 1.15, but it's going to get you pretty close to it if you wanted to do that. Oh, I already answered the next question right there. I didn't realize. All right, what percent did better? Well, the table tells you 88%, so that would be the bottom end side. Anything that would be on the other, you just subtract from 100 and you get the 12%. All right, question D. What percent scored below a 500? Now, usually when these tests are designed, that should be around 50% because they want the 500 to be the mean score, but there's the reality of what the data actually produces. Okay, so in our example, it's going to be close. It's going to be close to the 50%. You take the 500, which is the score that students got. You subtract the mean from it. That's going to give you a negative 14. You divide the negative 14 by, I'll just type it in here. So 500 minus 514, negative 14. You divide that by your standard deviation of 118. And you're going to get that number. Okay, so I went ahead and rounded it. I changed the 8 to a 9. So rounded there. Now, your table is not going to give you that much detail, but at least take what you can and you go to the table and you see what it tells you. All right, so I'm on the negative side here. It's a negative 0.119. So where are you? It's going to be around here. All right, so that would be, so this is close. This guy right here is pretty close to the 1, okay, but now if I round that up, it's going to give me 0.12. 0.12, yeah, it's still pretty close here. So the answer that I have in mind, I actually misread my table, went to the wrong spot. So again, authentic, changing some things here. It's pretty close to that number, the 46, but also heading in the direction of the 44. So I'll go ahead and just, it's somewhere between the 44 and the 46. Let's just call it, let's call it 45.5. We'll go with that number there. All right. Well, that answer sounds a little bit better to what I was trying to describe before anyway, that it should be close to 50%, and that actually pulled us a little bit closer. Hey, the tables are a little bit difficult to read. Man, they'll catch you on those. Caught me right there. All right, so E, what percent scored between 500 and 650? We get to put together a couple answers here. The 650 was the answer that gave us up to 88%. I'm gonna have to change my numbers here. The 500 was what I called 45.5%, which measured up to here. So I got up to 88 and then 45.5. So if I subtract those two, no, 42 throws me off because I had that number earlier there, but it turns out to be about 42.5%. It is within that range there. All right, in this last part here, what we're gonna do is work backwards. What that means is you're gonna get percentile scores, and then you're gonna backtrack to figure out what the actual scores were that went with them. So this first question says, it's more of an understanding of the idea what a percentile is. What would it mean if a student's math SAT score was in the 80th percentile? What that means is that they did better than 80% of all the other students who took that math test. And there were 20% who did better than them. That's what that means. All right, so if you had that information, the 80 percentile, and you want to know what their actual score was, or at least approximate it, what we do is we work backwards and we figure out the z-score and then use the z-score compared to the mean, and you can find the value. So what we're going to do is go to the table and look up 80%. All right, that's 86 way up there. So go back to the bottom. So it's right about here, and that's pretty darn close to 80%. It's just 0.23. So I'm going to go with that number and say that the z-score is 0.85. Okay, so the z-score that corresponds the best to 80th percentile is going to be 0.85. All right, now to calculate their score, to figure out what the actual value was, you can use this formula. So what we're trying to figure out is the data value, and now we've got the z-score, we know the standard deviation, we know the mean. So what we're going to do is multiply the standard deviation by the z-score, and that's going to tell us how far we actually are from the mean. So then if we add that to the mean, we can actually locate where that score would be. All right, so I've got it all worked out here, but let me break it down just to better describe what's happening in the middle there. Okay, so if I multiply the standard deviation by the z-score, see, the z-score is the number of standard deviations you are away from the mean. That's what it is. It's the number of standard deviations you are away from the mean. So if we have 0.85 of standard deviation, you can multiply 0.85 by the 118, and it tells you that you're 100.3 points away from the mean. Okay, so then if I add that onto 514, I end up at 614, which I'm just going to round down to 3, or round down to 614. All right, now if you're going to be on the bottom side, your z-score is going to be a negative number, and it'll take care of itself on there. So if you had a very low percentile, you automatically have a negative z-score. That get worked into there and do that. Otherwise, I don't know, it does it on itself. But if you forgot the negative, you should know which side of the mean score you are, if you're above or below. Anyhow, this one turns out to be 614. Over to the side, I wrote down 610 or 620 because when they do score SATs, they don't give you numbers like that. They always give you numbers that end with zeros to them. So it would have been one of those two scores. All right, we have another math student who got a 40th percentile. That means they only did better than 40% of the others who took the test. They're on the bottom side of things here. If you go look up that percentile, I suppose I could have just waited there to show you, but when you go look up 40 percentile, because it's underneath 50 percentile, you're going to get negative z-scores. So you have a negative 0.25. Okay, and then when you multiply the negative 0.25 by the 18, you're going to get a negative number. 0.25 is actually like a fourth, so it's a fourth of that, but it's going to be a negative direction. So when you add it to the 514, you actually end up with a smaller number, which is going to be 485. And again, I wrote it over here as 480 or 490 because they don't score things that look like that. All right, getting to the very end here. E. A third student's score was 2 standard deviations above the mean. What's the z-score? Well, that's a 2. That was kind of an odd question because it's such a simple answer, but maybe it's also important to go back to the fact that you're going to have these whole value type things. So if you're 2 standard deviations above, that means your z-score is a positive 2. What is their percentile for that? So you take that z-score 2 and you just go look up their percentile for that one.